Right on the money. 7 o'clock. That's right. That's the start of our class, and I know that because that light stops blinking in the back. This is a really great classroom for me, and I hope for you as well. There's a very advanced video capability here. We have a camera in the back there, and we have a camera in the ceiling here. And so what's going on is we are recording this lecture, and on e-learning you'll be able. There's a feature called Course Echo, and you'll be able to rewatch these lectures, or if you, gosh forbid, miss one, you'll be able to tune in, a few hours later and pick it up. I did this for the first time in comm systems in the spring, and most of the comments were really positive about it. They didn't ding me on the one that I thought they would, but there was a couple. The only negative one was don't record it and don't put it on Course Echoes because I never came to class, and I would have enjoyed it much better if I'd actually come to class. So I thought that was kind of an interesting. It was truthful, and I kind of liked the observation. But as I pointed out, this is electromagnetics, graduate electromagnetics, fields and waves. I've been teaching some part of this course for 27 years. I've been at UT Dallas for 25 years, and I cut my teeth on teaching in a university environment in grad school a couple years before it. And they threw an EMAG course at me when the professor got pneumonia and couldn't show up for class, and they scrambled, and I had to take over. It was not EMAG as an undergraduate is not a pleasant experience anyway, and when you miss the first 2 weeks and you've got this strange guy coming in, not the comforting Richter freeze that you wanted, it was even worse. But so I've really enjoyed EMAG. I will say one thing is, every time I teach this course, I see something new. I see some beautiful piece of nature, some beautiful piece of electromagnetics that I haven't quite seen before. The tone of the course, I believe this is a first semester graduate course. It's funny, how many students are in the RF sequence? How many of students think they're about to graduate in the RF sequence? That's not too bad. Many of you guys decide to wait to the very end. And in fact, it's funny because I've purposely set up this course so that it is, it's your beginning, your introduction to the discipline. As such, I try to make it about, 30% harder than 4301, our undergraduate course, our first year undergraduate course, which I also taught for a large number of years before the professor who used to teach this course was Jan van der Zeel, a really, really good guy, and he passed away late 90s, and so someone had to step in, and it was really with difficulty that I stepped in to take over for him. I did bring a slightly different perspective into the course. Back then, he was really happy when he had 4 people start the course and 2 people finish the course. And I didn't think that was fair because EMAG was a much more critical component of of electrical engineering. Clock rates going up faster and faster, and it was just more imperative than ever that a well-rounded master student has an intuitive and a quantitative appreciation for the electric field and the magnetic field and the voltages and the currents that arise from them. Okay, so it was my job, it was my challenge to make this accessible to a larger audience. And in the past, I've had folks that have come into the course without any, like a computer engineering background with no EMAG at all, and they've done pretty well. And then I've also had folks that have taken 4301 and maybe even 4302, and I've always been worried. I've asked them, have I wasted your time? And only once in the last dozen years have people said, yes, one person said, yes, you wasted my time, I knew everything. Most people have said, yeah, so you've shown it slightly different, you've shown enough of a different perspective that it makes it. So one of the ways that I've done this is, and I'll go over this in a little bit more detail in a second. I'm holding off pulling up the syllabus and going through it because whenever I start to do that, I'll get through 10 minutes of it and somebody will come in and I'll have to start all over. So I'll hand wave for a little while. we will cover all of electromagnetics up front, and then we'll do specific examples for the last 2/3 of the course. So I will get every piece of the puzzle, all 15 or so quantities, field quantities, on the table at once. Walk us through it. It's an inordinately long introduction to the field. One of the things that I'll do to make your life easier, though, is we will only do Cartesian coordinates. We're not going to mess around with cylindrical coordinates at all. And we're not going to look at spherical coordinates until the very end when we do antennas, when we have to do spherical coordinates because it's a spherical symmetry problem. And by that time, you'll be so darn bored of Cartesian coordinates that you'll be begging me for something different. Okay? So we will simplify greatly the mathematics in order for you to understand the manipulations, and you can understand the physical interpretation of all the myriad of field quantities and the symbols that go with it. If you have a cylindrical coordinate problem next semester, you will have no problem picking that up. Because the only thing that you'll have to do is pick up a little bit of the mathematics. Nothing else will change drastically. Okay, so that's worked really well. That simplification, that letting that happily slide off the table. That's worked out really well, I thought, over the years. Okay, so let me try to play with this system and pull up. Oh no, it's already logged in. That's probably not a good thing because it's not logged in as me. Okay, so let's see. 2 places that I want to send you to on the web. One is my website, which is this www.utdallas.edu/DLM. Those are my initials. Okay, and if you come down here, you'll see we have a web page 6316. That I've been adding to over the years. What is this with this tab? It's kind of obnoxious. Okay, so the syllabus is listed on here. Probably an out-of-date syllabus now that I come to think about it. So we'll give you a better one. Homework assignment, and then solutions to the homeworks, and recommended homework completion date. The first few lectures are going to come out of this handy little document called Working with Fields, Practical or Pragmatic Perspective. And this is just mathematics, the mathematics of fields and the mathematics of fields, scalar fields and vector fields. And I think you won't learn anything except you'll be exposed to my notation on things. So this is a I don't know, it's a dozen pages or so, nicely typeset, complete with some typos that you can follow, and then some other presentations and links as well that I've added over the years. And I set that up before I really, whoops, I didn't want to do that, did I? I set up that web page before I really learned too much about e-learning. So I'm kind of just shifting over into that. And I won't do a really good job on that, I'm afraid. But does everyone use e-learning? Has anyone not used e-learning? Good. It's a nice resource. It's a nice resource for me to communicate with you guys. And fields and waves 14. Why it's set up this way, I don't know. But 6316 fields and waves, fall of 14. And so I have on here, I've loaded up the syllabus, and I've loaded up all the homework problems that you'll have for the semester. Solutions are also found on my other webpage. Okay. There will be an icon down here or a line down here. Let me go to student view. There'll be an icon down here that'll be called Course Echoes. And starting about tomorrow, the lectures from prior times will be posted on there as videos. The format is fabulous because you have two cameras, you have a big screen, and this piece here, what's covered by the document camera, or what's shown on the slides up here, will be the dominant window. And then in the upper right will be a small talking head image of me. That's from down there. And I think that's really nice because if you've watched these old style videos with one camera and a person operating, you kind of get seasick swinging back and forth between the blackboard and the person. And it's really frustrating because I'm watching these things and I'm trying to catch the last term of the equations, and I've got to look at the professor's ugly mug. So this way it's kind of comforting. You can focus on the math and just glance up and every once in a while and be reassured that it is a person actually presenting this to you. So I think it's a really nice format. Again, I've been teaching this for so long, and I'm kind of excited about getting all the lectures in the can. Getting all the lectures recorded. And I don't yet know exactly what I'm going to do. I guess it depends on how many times I swear in the class. That's a joke. I haven't done that in a long time. Undeserved. but hopefully I'll find some way to disseminate that in an interesting and open manner. Right now you need to log into e-learning to see this, or you will need to log into e-learning to see this. All right, syllabus. Let me go through the mechanics of the course before we get started. Here are the ways you can get a hold of me. My office is on the top floor, that corner of the building, the northeast corner of the building. If you head on up there and look for 4.904 or my name, you'll find me. My office hours are, they're right on here. Mondays and Wednesdays at 4 o'clock. I teach a class earlier than this, and so it's early in that. It's also by appointment, so I know that some of you that's a difficult time to make. So get a hold of me by appointment. We'll have a TA for the class, and that person will hold office hours, and I'm going to try and schedule his office hours or her office hours for Tuesday and Thursday, or maybe Tuesday and Friday, and that way you'll have 4 days out of 7 that you can get in front of one of us live. Okay, and so to encourage you, this e-learning thing is really nice too because you can post a thread on it. You can post a question not just to me but to everybody. So to think about it, if you have a question, probably half a dozen other people have a question. If you found a mistake in my class in my notes, probably half a dozen other people did as well. And so you'll alert everybody to that, and we can talk it out. So that's kind of a nice. If you like it and you use it, I will too. I'll be monitoring that and try to do that. Try to answer that. I'll also be making announcements, like when exams are, for example, using e-learning, and that should go directly to your UT Dallas email. So if you don't use UT Dallas email, start using UT Dallas email because I'm going to assume that you do. Okay. Here's my webpage. Here's my email. My phone number's there. I never answer it unless I happen to be in my office and I happen to be free. My phone. I guess I talk on that phone maybe twice a week or something like that. It's funny now. If you call, it'll register on my cell phone or my email account, which goes to my cell phone, that somebody called. And if you leave a message, I'll actually read a really bad translation. speech-to-text translation of that. It's really humorous. You'll swear that you didn't swear, but in fact, text says otherwise. The prerequisites for the course, I assume, and I've told you a counterexample, but I assume that you've had some undergraduate electromagnetics background. Okay? And the reason for that is I learned my first EMAG class when I took my second EMAG course, and I took my second EMAG course when I took my third EMAG course. And so I'm hoping that you really, really learn the solid foundation for electromagnetics in this course. Be able to understand things and be able to make decisions based on your understanding of electromagnetics. Okay. We'll study electromagnetic waves, and in particular the transfer of information or energy, very similar things, the transfer of electromagnetic information or energy from one point to another point. Obviously, one example of that is a communication channel, but it could also be radar, it could also be a variety of other, it could also be the propagation of a laser beam, sun hitting a solar cell, variety of other contexts of electromagnetic radiation. The specific topics, we'll get right into Maxwell's wave equations. I don't know how I'm going to teach that without hiking back and forth along the back blackboard. I'm tethered to my notes page. That'll be an interesting, clumsy experience for me. Usually I'm pacing back and forth, but I have to calm myself down. There are four, basically we will look at the four Maxwell's equations in differential form as our starting point. And I'll generally open those lectures, just as is fair warning, what's your favorite Maxwell's equation? So that's how you'll get to know them so well that you won't even worry about memorizing them. You'll just know them. We will understand each term in them by working with them, by looking at them, by reading them, by solving them and looking at their solutions. We'll understand those terms so well that we'll have an insight into the interplay of the electric field and the magnetic field in response, for example, to a current. Okay. So we'll study Maxwell's equations. We'll solve them. The simplest solutions are plane waves. This is where I'll start to tie in concepts that you'll have had in signals and systems, the Fourier series, Fourier transforms, and things of that nature. You'll see that most of Maxwell's equations, for most situations, are linear, time invariant, and so it dovetails really, really well with all the signals and systems, signal processing that you've also seen as an undergraduate. And that's a distinction from a traditional EMAG class. A lot of times, an EMAG course in an electrical engineering department is going to be taught by a physicist, and they're not going to have that comfort with signals and systems. That's not going to be burned into their soul the way it is for electrical engineers. And that really shortchanges us. Because if you can tie into the stuff you've learned from Fourier series or the stuff you've learned in convolutions, it opens up a whole new way of understanding the material in the course for the better. Okay, so we'll do that. Propagation of that plane waves, transmission lines is sort of a simple example of the same. Then we'll get into antennas, and then there's usually a couple of lectures left over, and I get to do whatever I want to do. We'll see. We'll see. Those are gratuitous lectures for me. Keep us entertained. Keep me entertained, maybe. Right now, the learning objectives, Maxwell's equations, wave equations, plane waves, all the manipulations associated with them. Taking these plane waves and bouncing them off surfaces so they reflect, some of them transmit. Boundary conditions, solving a differential equation, then solving a differential equation with respect to boundary conditions. It's another way of thinking about those topics. And at the end of the course, maybe the last 3-4 weeks of the course, we'll go into antennas. And again, if you go back to sort of the differential equation perspective, what that means is we now solve the forced equations. Instead of the, in differential equations, you had the homogeneous solution and then the particular solution. One was the unforced and one was the forcing term, the driving term. And that's all an antenna does. Right? That's all the antenna does. And that's why convolutions pop out so nicely from that perspective. And so the convolutions will be in space, X, Y, and Z, instead of in time. Okay? But other than that, it's very similar. And so I'll walk you through all that, and you'll see the mechanics of the mathematics, so you'll be able to perform calculations. But it's also my goal that you understand the intuition of that, so that you can make decisions about whether things work or whether things are worthy of calculation before you get started on it. And again, that's sort of the level of a graduate, student. There are 2 textbooks. Did anyone bring the textbooks? I don't blame you. They're really thick and heavy. One of them's really thick and heavy. Balanis. This may well be the last year I use Balanis. It's a great reference. It's a great textbook. It covers everything you want. Unfortunately, it just doesn't. It's just a little clunky with respect to the way I teach it. So you're going to be you may actually be a little frustrated with trying to track my lectures into Balanis's lectures. You may find that I spend 3 lectures and Balanis spends half a page, or you may find that I spend half a lecture and he spends 20 pages on it. Okay, you may find that it's all out of order. Okay, and again, we've been dealing with this for a dozen years, and it's worked. Yeah, question.
So, is there another book that would be a good supplement?
Is there another book that would be a good supplement? Is there another book that would be good? There are 20,000 electromagnetics books out there, and my lectures draw from about 12 different ones, and so you'll see me change notation slightly here and there, nothing too bad, I hope. But what I've done is I've pulled from textbooks. This text. Lorraine Corson does a great job on waveguides. I'm going to lecture out of Lorraine Corson for the waveguides. This other guy does a great job on transmission lines. I'm going to lecture out of him for transmission lines, and so that's what you can start to do as well. Pick and choose and find. Just because I think Lorraine Corson does the best job on a certain topic doesn't mean you think that, right? So some of us like certain authors and some of us like other authors for the same mystery story, right? And so it's just a question of taste and background. So make use of all the other textbooks out there to learn from. Even I'm sure there's even great stuff on the net as well. I also require the Slater and Frank. How many of you have picked up Slater and Frank yet? That's not heavy at all, is it? That's not expensive at all, is it? What's it going for now? $15? $6. Oh, good. It's gone back down. I love it. It was up to about 12 or 14 at one point. Now it's down to 6. It's a Dover edition. It's a paperback edition. It was first published in 1948, I think, 1949. And just to give you a little bit of background on why this is such a lovely book, the Slater and Frank ran the radiation laboratory at MIT during World War II, and that was the laboratory that really did all the work on radar. After the British sort of demonstrated it, a lot of the engineering advances in a very, very short time really came out of the radiation lab at MIT, and Slater and Frank led it. And this was their view after using and employing the electromagnetics hands-on, from a theoretical perspective to a hands-on demonstration, all in the same days, all in the same handful of years. They really understood practical electrical engineering of electromagnetic systems. And then they wrote a book about it. And this book was designed to teach. It was not designed to impress other professors. So it's a beautifully nice thin little paperback. I discovered it in graduate school when I was struggling through my first graduate EMAG class, and I was up in Oregon, and I got out of rainy Portland and I went to rainy coast of Oregon, and I hung out in a old cheap motel by the shore, and I just read it cover to cover, and it just made sense to me, and so it's just a beautifully well written, simple, no airs about it kind of a presentation to electromagnetics. And so I present it to you as a required text in that light. When you're getting frustrated with not seeing the big picture, some point in the semester you're going to be down in the weeds, not understand, buried too much on details, and you're losing track of the bigger picture. That's the time when you want to take a break and sit down and start reading Slater and Frank, and have it all come together on a nicer plane. Or I don't think you can really do this, but one way to do it is wait till the end of the semester, and this is a good way to study for the final. Or it's a good way to study for the midterm. Or it's a good way to spend this weekend, dusting off your undergraduate skills. It's up to you. But it's a very, very accessible, it's not trivial. It's not an electromagnetics for dummies. It is just a very clear, nice treatment of the subject matter that leaves off a lot of the stuff that's you don't have to mess with the first time around. Okay, and then I also have this introduction to the mathematics. So I've changed things around a little bit in this class. I used to last year, for example, and all the other years, I used to have a take-home midterm, and the take-home midterm took you 10 days, and it was a pretty extreme experience. And I intended it that way. It was a great learning experience, and it was a great way to learn, to show me that you could learn new subject matter. Unfortunately, and then I also had a take-home computer project, which was not a very difficult computer project. It was just the emphasis was on learning, on learning certain things. And then that was a report due at the last day of class. But unfortunately, and then this really saddens me, there was a lot of academic dishonesty that came to light the last year I taught it, and so I just can't have. It's not fair to the 90% of the class that's honest and does their own work to have people buy answers online to the midterm. So unfortunately, everything will be in class, and that's kind of I don't like it, but it's the only fair solution that I have. So we will have a midterm somewhere about 2/3 of the way through the course. We're such a slow start. I go through all the basics so slowly and so in such detail that it takes a long time to get to a point where I can actually ask questions. So it's not going to be in a month. It'll probably be 6 to 7 weeks from now. It'll be a good 2/3 of the way through the semester before we have the first midterm, the midterm. I'm going to go over the homework. I'm going to give you all the homework problems, some out of Slater and Frank, a lot out of Balanis. I also give the solutions to those. Okay? And on the last day of class, we're going to have an in-class quiz or an exam where I'm going to ask you some questions on the homework. In fact, I'm going to ask you homework questions, and that's going to convince me that you've done the homework. Closed notes, closed notes, closed book, closed notes, no calculator. I may relax that for the final exam. I may allow notes and books for the final. I haven't decided yet. I can be persuaded. How's that? I'm not sure you want to persuade me, but I could be persuaded on that. And then the final exam will be on the day of record for the course. So during exam week, at the official time and place, we'll have the final exam, and that'll be cumulative. Okay. So if you just take a look at these rubrics, the midterm counts for 30%, the final counts for 40%, and the homework counts for 30%. You'll also see that the way I've phrased it is an exam on the homework and the computer project. And I haven't quite figured out how I'm going to do that, but I'm thinking, give me some time to kind of wrap my brain around it, but I'm thinking of assigning the exact same computer project. Maybe you'll make it a little bit lighter, and have you do that, and then I can ask you questions about it afterwards. That would make it pretty easy, you know. Again, it's not my intent to make this a ridiculously hard course. It's my intent to make it a very valuable course for you, where you actually learn a lot. Okay? All right. All that other stuff. Now, back to Blackboard. Back to e-learning. Here is the homework problems. And these are for the second edition. Does anyone have the first edition?
It's like $20 on Amazon, so it's much more.
Okay, so if you go here, here's your homework assignment if you're using the first edition. Okay? And here it is for the second edition. Same problems, the numbers have been slightly changed. So if you want to go $20 on Amazon, I would recommend that route and do the homework problems from the other that are listed on the website. But officially it's the second. Okay? And so chapter 1, chapter 2, chapter 3, 4, 5, 7 and 8. I can't count very well, I guess. And then there's some problems from Slater. If you go back to my web page, you'll see I have files of the solutions. This one's particularly nicely typed up, which means it's neat and easy to read, and there's probably typos in it. This is not less so, but there are problems in there, and several versions of it. Over time, I've forced my TAs to write solutions again, so that the idea is that they present it in slightly different ways, with slightly more explanation or less explanation, and even some Slater and Frank solutions are up there as well. Now, what I recommend is you don't use these solutions. I recommend you don't use the solutions. I recommend that you work with teams and really understand what you're doing, and really, pound it all out. And then if you need to check your answers, or you really, really get desperate, it's there. But you should own the homework problems. Most of them are not that difficult. Okay. This may be useful to you. This was back from 2009, but things haven't really changed all that much. A few days here and there doesn't matter. But this sort of tells you where I think you should be. The end of September, you should be pretty much through, chapters 1 of 2 of Balanis. Mid-October, chapter 3. End of October, chapter 4. Chapter 5, November 16th. End of November. So take that with a grain of salt. Somebody asked me for this probably back in 2009, and so I put something down, but it's real approximate. Okay. And then this is what I used to ask on the computer. This computer project is what I used to ask. It's there. You can feel free to look at it. I will make a modification of it, and I will introduce it at exactly. There's a time when that just slides right into the lectures, and when that happens, that's when I'll introduce it. Okay, but there's no secrets. You can happily take a look at that. Okay, I think that's all the mechanics of the course. Did I miss anything? Are there any questions or concerns or worries? No one's gotten up to leave that I've noticed. Anyone want to get up and leave? Good. Good. I don't want you to leave. I want this to be a really good, positive experience for you guys. Okay? Any other questions, comments? Where are we? Okay. About 40 minutes left of class. I'm going to get started. Is that okay? All right. So I'm going to go over I'm going to go over the mathematics associated with fields. Now, the name of this course officially is Fields and Waves. And so it stands to reason that I should go over at least a little bit what a field is. Now, I didn't come up with the title of the course. I don't have any problems with the title of the course, but really what it is it's electromagnetic fields and electromagnetic waves. Okay. Of course, you can extend it to a variety of other types of fields and waves, but we're going to focus on the genius of Maxwell. Okay. So it's nice to know kind of what we talk about when we're talking about a field. And so I'm going to refresh your memory probably from signals and systems, where you had signals, voltages, and currents, presumably, usually. If you're talking about temperature and it's an electrical engineering course, you're going to run it through a transducer and have a voltage reading. So you're going to have some sort of a function or a signal, and it changes with respect to time. So everything you did there was everything in signals and systems, and most of your undergraduate electrical engineering degree had to do with voltages and currents that changed as a function of time, or signals that were changing as a function of time. Now, my mathematician friends would throw stuff at me and get all mad at me, but my simplistic and simple way of thinking about this is that these scalar functions go to scalar fields, and there what we're going to talk about is something that depends on space as well as time. Okay? Nothing fancy here, nothing difficult here. I'm just introducing what I mean by a field. Okay? And then I'm also introducing what I mean by a scalar. So a voltage is a function of time, a current is a function of time. Those are just quantities. Okay, 7 volts moving to 6 volts, moving to 5 volts, moving back to 6 volts. That's just a number that changes as a function of time. So this is just a number that changes as a function of time and space. And I've been even simpler because, as I mentioned earlier, I'm writing space as Cartesian coordinates, x, y, z. Okay. And the time I'm just throwing on there because it's probably going to change with respect to time. But what makes it a field is this x, y, z stuff on it. Okay, that's what I mean when I say a field. And let me give you an example right off the bat of this. Early in my career, I was working with very high power pulse energy systems, making sharp. It was a light source. It was a really fancy light source, and so I was creating a plasma between these two electrodes, and so I would charge up a bunch of capacitors, and then I'd throw a thyrotron or a switch. And it would, and all the power that was stored in these capacitors would break down the atmosphere and light it up like you can't believe. Very, 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 very high fluences, intensities, watts per meter squared, watts per meters per steradians, meter squared per steradians. Really fun, really dangerous, really big LRC circuits, right? And these capacitors, the small ones were about this big by about this long. And the bigger ones were bigger than that, big sizes of, I don't know, they used to call them jerry cans that you would put petrol in, you put on the back of a Jeep, big, they call them literally jerry can capacitors, right? And so they would store, they had reasonable values of capacitance, but they would store kilovolts of voltages. So 1/2 CV squared was a lot of joules. And so if you had to store these capacitors with a wire across the leads because you couldn't, they'd charge up from static electricity, and if you happened to touch it and it was charged, you'd die. I mean, it was, you know, if you ever had, it was really kind of fun. If you ever had these charged, your circuit went wrong, you'd have to take a big old screwdriver, wrap it in insulation, and gingerly touch across the electrodes, and it would break down with a huge pounding, loud noise. Really fun, really dangerous though. And so what we would do is we would use maybe 20 or 30 of these capacitors, and we were orderly engineers, and so we'd line them up, you know, in the X direction, maybe 5-fold, and then we'd stack them up in the Y direction, another 5 across, and then we'd stack them up back in the Z direction, another 5 across or so, maybe 3 deep or so. So we'd have a couple by 3 by 5 kinds of arrays. And we would label and assign each of these capacitors with a location, a number for the X, a number for the Y, and a number for the Z. And so associated with the voltage on each of these associated with the electrodes on each of these capacitors, at a place X, Y, and Z, over, up, and in, was a voltage. So that voltage on that capacitor was, you could think about that as a field of capacitors that as part of your circuit. And these were big enough that when you wired your circuit together, you know, you were sort of on your back with a wrench, wiring the copper strips onto it. The old days. But that gives you a visual thought process of what we're talking about when we extend the voltage on a capacitor. How could that ever be a field? Well, if you have enough of these capacitors and they're all wired in together like that, it makes sense to treat them as, you know, an ordered structure of numbers, of voltages located at different spots in space. Okay, and the Cartesian X, Y, Z was a natural coordinate system for that assignment. Okay, but that's just a voltage. So we also had vector functions, and I really honestly don't know how much you remember on this as an undergraduate, but you know, one function that you might have thought about was a force. You know, one vector that you might have studied was a force, and forces. You know, forces have a magnitude, how hard I push something, right? And also it has a direction. So I'm pushing it this way versus this way with about the same amount of magnitude. So if a scalar is just a number, a vector is a number plus a direction, a magnitude and a direction. And this is just a point of notation. I discriminate between a scalar and a vector by this little scriggly scrawl right underneath my letter. Okay, so you see that horrible little scrawl right there? For some reason, way back, that's how I decided to draw with my crayon and my paper what I would look at as a vector. Okay, you'll see countless. Bolanis doesn't use that. You know, you'll see countless other ways of doing it. A lot of textbooks use bold print, but sometimes the bold doesn't look so bold to me. And so that's, you know, sometimes I kind of stress out about that a little bit. So that's another reason why I like sort of the redundancy of that. Anyway, the same way that scalar functions go to scalar fields, our vector function will go to vector fields, and at any position in space, I'll have a magnitude and a direction. The direction will also point in space as well. Think this take a break for a second and talk about the weather, right? If I think around the campus, or I think around the DFW area, or I think around the country, whatever longitude and latitude I go, northings or eastings that I go along the continent in North America, that's an X and a Y. And at any instant, on the surface, I will have a temperature. And so that's a temperature that's a function of X and Y. So if I go over here to the super target out in the parking lot, that location can be determined by an X and a Y, a northing and an easting, a GPS coordinate. In the old days, we used to call them northings and eastings. And then if you go up from there in the Z direction, 100 feet, 1,000 feet, 2,000 feet, 50,000 feet, your temperature changes again. So your temperature across North America is a field, but at any point in space, any X, Y, and then Z in space, you've got just a number. 100 degrees, 40 degrees centigrade, 0 degrees centigrade, minus 40 degrees centigrade. Somewhere up in there, you just have a field. Okay. Same weather system. That temperature is going someplace, right? And it travels by convection, which we call wind. So you have velocities. You have wind velocities at any instant of space. So in the super target parking lot, I have a nice, gentle breeze that lowers the apparent temperature from 40 degrees C down to a balmy 39.5 degrees C. Right? Maybe in Texas it actually makes it hotter, I don't know. But if I go up, I'll have a different wind velocity. And so at any point in X, Y, and Z space across the North American continent, I've got a wind speed, I've got a wind velocity that is a vector, that is the speed and the direction that it's going in. A southeasterly gale blowing at 40 knots, for example. Or in the atmosphere, the jet stream is going at a different speed. Okay? So those are simple examples out there of a scalar field and a vector field. Okay? Now, whenever I see a function or a signal, whenever I see a field, I have this uncontrollable urge to take a derivative. You're laughing because I know you do too. Whenever you see a function, the first thing you kind of want to do is, well, maybe these days you want to plot it. But in the old days, and after you plot it, you want to take the derivative, right? So let's talk about that. If I have a scalar function u, the only thing I can really take its derivative of is time. And it's pretty easy to know that the derivative of that scalar function will be d by dt. And I can write this in a variety of ways. Some of these you've probably seen before, some of these you haven't. But, d by dt operating on u will give you the first derivative of a scalar function or a scalar signal, the rate of change of the voltage with respect to time. You can write it with a little dot over it, which I don't usually do, because the dot gets lost, with my sloppy penmanship. And sometimes people like to do a little subscript t, especially when they're working with partial differential equations. I don't generally like to do that either, because I have other designs on my subscripts and my superscripts. Okay? So I don't usually like to do that. So you may see those in certain textbooks. I won't really do those. Now, what about a vector? So we'll just think in terms of a vector. We'll think in terms of this vector function, f as a function of t. So if I write this vector function If I write that vector function a little bit more explicitly, this force on this microphone has a direction and a magnitude. That direction and the magnitude can be broken off into an x component, a y component, and a z component. Okay? The nice thing about that decomposition is that f sub x, the x component of the force as a function of time, this is a scalar function. The y component is also a scalar function. And the z component is also a scalar function. If you're keeping score, the vector function is 3 times better than a scalar function because it's got 3 pieces of information in there. Okay? You can imagine the taunting that goes on in your textbook about that when you're not reading it. That's a joke. Not a very good one, apparently. So if I look at this vector decomposition, I should also point out these are unit vectors, ax, ay, and az, and that's just the way I choose to write my unit vectors, with a little a, the direction that I'm caring about, and a hat or a caret over it. Again, that's just my notation, and you'll see a million other. Some people like I, J, and K. Some people like E's with hats over it or not hats over it. I just happen to like a sub x, a sub y, a sub z, a sub r, a sub theta, a sub phi, things like that. Okay. But anyway, if you take a look at this, it becomes pretty easy to figure out how to take a derivative of a vector function, because we already know how to take a derivative of a scalar function. So the derivative whoops. So the derivative of a vector function is a piece of cake. Okay? And the emphasis that I'm trying to make is that word, the derivative. In other words, if you're dealing with just things that are a function of one variable of time, you don't have to sweat too hard about what you mean by the derivative. Okay? Now when I look at fields, it's easy to take a derivative. But what do we mean when I say, no, I don't want a derivative of a scalar field. I want the derivative of a scalar field. Okay? Is x better than y, better than z? That's the value judgment. That's the value judgment that I want to talk about. Okay? So let me talk about taking the spatial derivative of a scalar field, and I'll leave off time here. Okay? I'll leave off time because I want to emphasize the space part of it. So I want to take the spatial derivative of psi. And we know about partial derivatives. So I know that I can take del psi del x. And we also know that we can take del psi del y and del psi del z. a spatial derivative might be del psi del y. A spatial derivative will be the partial derivative del psi del z. But I don't care about a spatial derivative. I care about what the spatial derivative is. Now, whatever psi is, the voltage on the capacitors, or the temperature, measured by a weather balloon above, 5 miles above Lubbock, it doesn't care. It doesn't know. The system doesn't know my x, y, and z. And in fact, if we don't collude, if we don't talk, my x, y, and z is going to be different from your x, y, and z. But when we talk about the derivative, they better match up. Right? If you pick one coordinate system, and I pick another coordinate system, and I want a quantity that's called the derivative, it better be the same number. And it better be irrespective of what the temperature thinks. Because the temperature, the field from Maxwell's equations, the voltage field, the temperature field, it doesn't care about us. It doesn't care about our coordinate system. It's not in its mind. So which is better? Which one of these things are better? The answer is none. They're all equal components to a derivative, to the derivative. And so each of these partial derivatives is of equal importance when I talk about the derivative. I have to separate them out, right? I have to separate them out because if I just have 3 slopes, 7 volts per meter, 2 volts per meter, and 3 volts per meter, I can't just add those up and get 12 volts per meter because I'm losing track of information. I'm losing track of which one was the biggest and which one was the smallest. That's something that I don't want to do. So I have to tag, or I have to keep track of. When I put these guys together, I have to keep track of which one was which. Which one was the 7 and which one was the 5. Whatever numbers I used. Which one was the 7, which one was the 3, and which one was the 2. And the way I do that is I use my unit vectors. Which is really kind of nice because remember those unit vectors, x versus y versus z, right? Those unit vectors were at right angles. And right angles are pretty magic. Pi over 2, 90 degrees, that's pretty magic because they're orthogonal to each other. A dot product between any of those is 0. So what's going on in the x is independent of what's going on in the y, is independent of what's going on in the z. So they make the perfect tag. They make the perfect little label to keep track of those 3 subcomponents of the derivative of that scalar field. So the derivative of that scalar field is just the sum, the sorted sum, del psi del x in the x direction, del psi del y in the y direction, del psi del z in the z direction. And that's so useful and just so long to write that we'll give it that notation. And that's called our del operator. And I think you can, if you've parse this and this, you can identify the del operator. At least in Cartesian coordinates, as d by dx tagged in the x direction, a sub x, plus d by dy tagged in the a sub y direction, plus d by del by del z tagged in the z direction. So this del operator just goes around looking for all the scalar fields like a little Pac-Man, just pop, 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 looking for a scalar field to take the derivative of, to take the spatial derivative of. Okay? And maybe the most startling thing about that, at first glance, which we'll resolve in a second, is that if I start with a scalar field and I want to take the derivative of it, somehow, without us thinking about it, that scalar field was transformed into a vector field. The derivative of a scalar field becomes a vector field. So the derivative of the temperature distribution, the temperature field around, over North America, is now no longer a scalar at every point, but it's a vector at every point. Okay? That just happened naturally. That transformation, just from a vector field from a scalar field to a vector field, just happened naturally. Okay? And it just blurs the line, I think, beautifully, maybe troublingly, but beautifully, I think, between scalars and vectors. Okay? So you have to keep track of what you're doing, but notice that when we work with Maxwell's equations and when we work with our laws of electromagnetics, we're going to be sliding back and forth between vectors and scalar fields all day long, just from the simple act of taking the derivative. Now, if we pause and we think physically about what we're doing, if we have a function and we take its derivative, at a particular point, we're measuring, what are we measuring on that function? What's the derivative? What's the physical meaning of a derivative at a particular point? The slope. It's the slope, right? It's the instantaneous rate of change, which is, in a sloppy, nice way, the slope. Okay? And so now if I've got a contour, I've been using this analogy for 27 years, and someday I'm going to get in trouble for it because it's not perfect. Okay, but if I'm going to let's say I go. Texas is a bad place to think about this, but supposing I go to Colorado or someplace where they have mountains, or at least hills. Like maybe there's a couple of hills around White Rock Lake or down in Oak Cliff or someplace. So you now have a height that's a function of x and y, northings and eastings, or the position of your map. You have a height. If you're at the top of Pikes Peak in Colorado, you're at 15,000 feet, more or less. If you're in Denver, if you're at the location of Denver in x and y, you're at 5,000, 6,000 feet, mile high. Okay, and so now you've got now think about what happens if we hike to the top of a hill, and this is where being constrained by the podium is really messing me up right now. I'll have to go off camera a little bit. So here we've got this contour of land, right? The stage comes up, the podium comes up, and it drops down, and then it drops down even further here into sort of a little bowl. Well, imagine this as sort of a continuous contour of height. And so what I can do is I can find the slope of this height. And so at any particular point, I can measure the rise over the run, the slope in the x direction and the y direction, and I'll get slopes in the north, lined up with the north, lined up with the longitude, and lined up with the latitude. Okay? And those will be terms of the spatial derivative of the height as a function of east and west, or longitude and latitude, or x and y. If I add them together to get the spatial derivative, what I will find is the slope, the direction of the biggest slope. So if the entire rate of change of the terrain is in one direction, like off of a cliff, I'm going to get a huge number in that direction and zero number along the cliff. On the other hand, if I've oriented my axis so that I'm at 45 degrees from that cliff, I'm going to get the same amount. But now if I vector add them up together, I'll get the same magnitude of going from up on a cliff down to the valley. Okay? So the way I like to look at it is if I'm on the top of a hill, or if I'm in a terrain, and I'm hiking, and I've got my canteen of water, and I pour it out, the direction that the water flows is this first derivative. Is the first derivative of the height as a function of space. Okay? I guess nowadays what you have to do is you have to take off your camelback and then spray it down a little bit, so it's not as easy as just taking a water bottle. You're hiking with a water bottle and you pour it down. And then ostensibly the speed perhaps of how the water flows can be related to the magnitude, perhaps. Okay? So that gives you a physical interpretation of the spatial derivative of a scalar field, and in particular, in words, we call that the gradient, or the grad of phi. Okay? So it measures the slope, and the direction is in the direction of greatest slope. Okay? So that gives you a nice physical interpretation for what we mean by the gradient. And it also gives you sort of a nice heuristic, hand-waving argument of where it comes from and why we might be interested in it. Okay? Now notice that I'm only talking about Cartesian coordinates, but nothing I've said changes too much when we go to other coordinate systems. The whole form of this operator may change, but you can figure that out when you need to. You don't need to figure it out now. The other thing to point out is that this del operator is actually a vector in and of itself. Because if I look at what the del operator is, it's d by dx, a sub x, d by dy, a sub y, d by dz, a sub z. It has the unit vectors in there. So the del operator has the vector nature in it, which is why the derivative of a scalar becomes a vector. So it didn't happen right out of the blue. We label the del operator, we see the del operator as its own vector, and whatever it touches like a vector. Okay? So if it touches a scalar, that scalar becomes a vector. Okay? Now, we have just a little bit of time, so I'm just going to set this up. So the del operator is a vector. And I want to look at its interaction with another vector, and that's the vector fields that we were talking about. Okay? So we asked, if we have a scalar field, what is the derivative of a scalar field? And we found out that it was the gradient. And now if I have vector field, what is the derivative of the vector field? And the way to approach this is to say, well, there's something neat about the gradient, about the del operator. The del operator has in equal parts a derivative in the x, a derivative in the y, and a derivative in the z. So since there's no other dimensions in space, in physical real space, but x, y, and z, sticking with the del operator makes some sense. So we ask, I have a vector. Okay, it's a vector operator, but it's still a vector. And I've got a vector field. And I want to combine the information associated with the vector operator with the information associated with the vector field. I want to collide those things. I want to mix the information of the vector operator del and the vector field f together. And when I use those words like mix or combine, what mathematical operation in general am I thinking about? Multiplication. So if I multiply this vector operator with this vector field, I will mix the information of the derivative with the information of the vector field. Question for you. How do I multiply two vectors together? Cross product and dot product. I have two choices. I therefore have two types of derivatives of vector fields. I have a dot product and I have a cross product. So I have del dotted with f, and I have del crossed with f. So there are two possible first derivatives for vector field. Okay? If I dot product two vectors together, do I get a vector or a scalar? And if I cross product two vectors together, do I get a vector or a scalar? Okay. So the short, simple answer to which one you pick is going to be which one you want. If you want a scalar quantity, you do the dot product. If you want a vector quantity, you do the cross product. Okay? Now, next time when we come back, I'll turn the mechanics of this and I'll tell you a more rigorous answer. But that's my little cheat sheet to you guys and use it shamelessly. I do. That just helps you keep track of which one you want to be using. Okay?